Norton's theorem is pretty much like Thevenin's theorem, but it states that a portion of a circuit can be replaced at any terminals, can be replaced by a current source and a parallel resistance. In Thevenin's theorem, it was voltage source and a series resistance. Here it's a current source and a parallel resistance. So let's say this is a circuit and we want to replace this part of the circuit from this terminal using Norton's theorem. So we will essentially get a current source according to Norton's theorem. The whole part, this part from this terminal, can be replaced by a current source and a parallel resistance. So if this terminal is A and B, this is still A and B, and the remaining part can be reconnected here. So we will get the same response here, that is same voltage drop across the element or current through the element. So how do we get the current, the value of the current source? That we get is we first disconnect it here at the terminal, and then we short circuit this. This one is short circuited, and we find the short circuit current. In Thevenin's theorem, we used to disconnect the element and we would find the open circuit voltage. Here we disconnect and short circuit it, and then we find the short circuit current. So that's how we get the Norton's current, which is the short circuit current. This one is Norton's current. And how we get the resistance Rn, we can call it Rn. This is exactly like the Thevenin's theorem. So we remove this one and we just find the resistance seen from seen from here. So that will be Rn, which is the resistance here. So exactly like Thevenin's theorem, just the current is different. Finding the procedure to find the current. So here is an example. I want to find the Norton's equivalent circuit, and then maybe here this is another let's say we have something connected here, a resistance, let's call it R. So we want to find the Norton's equivalent circuit at this terminal. So basically we want to replace this part of the circuit using Norton's theorem. So what first we will do is we will remove this one and we will short circuit this part. So this will be now shorted out and we will find the short circuit current here. Now when we look at this part of the circuit, we can see there is a voltage source, a series resistance, and this one is a current source and a parallel resistance. So for the ease of finding, what we will do, we will convert this current source and the parallel resistance into, we will do source conversion basically. So we will convert it into a voltage source and a series resistance. So the polarity will be like this, since the current was flowing in this direction, voltage is like that, and this will be, so this is 40 ohms, which is this one's, this is the converted circuit, and the value of the voltage source will be 40 times 2, which is 80 volts. So that's there, and this one stays as at 20 ohms. This is 120 volts, and we have this 12 ohms is there, which was this one, and we want to find this short circuit current. So this is our ISC, which is I Norton. So let's call it IN. Now as a result of the short circuit here, this resistance, this 12 ohm resistance is virtually shorted out. So we don't this resistance has no meaning in the circuit because these two terminals are shorted out. So we have this 120 volts here, 80 volts here, they are in opposition, and we have two series resistances 40 and 20. So we have basically the current ISC or IN will be 120 minus 80 divided by 20 plus 40. 20 plus 40. These two voltage sources are in opposition, so they will be subtracted. So that's 40 here and this is 60 here. So basically we have the current 2/3 amps. So that's the Norton current or I short circuit. So our Norton circuit will look like this one, 2/3 ampere. And now we need to find the resistance here. So what we will do, we will we can do two things. First of all, we can actually calculate the resistance using this circuit or this circuit. We will get the same result. Let's see how that happens. So I will actually draw the circuit again, so that will be better, I guess. So instead of, that's very clumsy there, so that's there. This one is 40 ohms, 2 amps, 20 ohms here, and 120 volts there, and I have 12 ohms here. So I need to find the resistance seen from here, as seen from here. So when I did the source conversion thing, the circuit became like this. So this was there, this was there, there was this voltage source, and the resistance value was the same, and this was 12 ohms there. So basically it was the same here. So that's, the resistance is 40 ohms, so 20 ohms, 40 ohms, and here it was 80 volts. Now when we want to find the resistances, the resistance in this circuit, we have to make the sources inactive. So the voltage source will become short circuit and the current source will become open circuit. So let's do that first for this circuit. Let's do the voltage source. In order to make it inactive, we will short it out. So this will be short circuit here, and the current source will be open circuit. So I will just remove this one, it stays like that. So what we have now is, we have 20 ohms here, 40 ohms here, they are in series, and when I'm seeing here, the circuit becomes like this, 60 here and 12 here, and here I am trying to find the resistance. So basically my resistance now becomes 60 parallel 12. So that is 60 times 12 divided by 60 plus 12, which is 72. So that becomes 10. So 10 ohms. This is 6 and then 10 ohms. This is what I am getting using this circuit. Using the converted source converted circuit, we will get the same result basically. So in this one, we will again make the sources inactive. So there are two voltage sources, both will be short circuit. So basically we are getting the same thing here. This is short circuit, this is short circuit, so we are getting 20 plus 60, 20 plus 40, which is 60. So 60 in parallel with 12 ohms, so that is the same. It has to happen because we are not changing anything when we are converting the sources. So this is our Norton circuit as seen from that terminal, which was called AB. Now whatever was, there was nothing connected, as we just said a resistance R was connected, but if we had a value, we could now calculate the current through it, or voltage across it, so voltage drop across it. So basically that's just an example.